Okay. Today we are discussing. Yes, students. Today we are discussing. Unit 13. Unit 13. Unit 13. Eurasian's metrization. Eurasians. Eura- Eurasians. Eurasian. Eurasian. Metrization. Metrization. Theorem. And stone sec compactification. And stone 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 sec CECH stone sec compactification 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 concepts definitions definition 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 metrizable spaces metrizable metrizable page number 112 page number 112 metrizable spaces metrizable spaces a topological space x comma t a topological space x comma t a topological space x comma t means tau, that is not t, tau, is said to be metrizable, is said to be metrizable, metrizable. If there exists a metric D, if there exists a metric D, metric D on X such that the topology induced by ST means such that the topology TP means topology induced by induced by induced by pencil induced by the topology induced by the metric D on X induced by the metric D on X metric D on X metric D on X is same as the original topology. Same as the original topology. TP means topology, original topology. Tau on X, read as tau on X. Tau X. Example. Example. Every metric space is metriable. Every MS means metric space. Every metric space is metriable. Metriable space since the topology space. The topology on A since the topology TP means topology on a metric space A MS metric space is defined by the corresponding metric is defined by the corresponding corresponding metric. The corresponding metric. Next, one theorem based on this one theorem. Metric space based upon this theorem one theorem. That is page number 113. Theorem. Theorem. Let R power of infinity be the product space. Prove that or prove that. Let R power infinity be the product space consisting product space, product space consisting of all sequences, consisting of all sequences consisting of all sequences of real numbers of real numbers endowed with the usual topology, endowed with the usual topology, TP means topology, usual topology. Then R for infinity is a metrigible space. Then R power infinity is a metrigible space. Metrigible space. Metrigible space. Proof. Proof. For any A comma B belongs to R, for any A comma B belongs to our set of real numbers, define D A comma B, define, define D A comma B, A comma B equal to minimum of mod A minus B comma 1, A minus B comma 1. Then you can easily verify D is metric on R. We can easily verify that. Easily verify that D is D is metric on R. D is metric on R. Metric on R. Now for any x equal to sequence of xn and y equal to sequence of yn, which are belongs to set of real numbers. Set of real numbers to infinity. To define dx comma y, dx comma y, dx comma y equal to supremum of n belongs to z, n belongs to z plus dxn comma yn, dxn comma yn whole divided by n divided by n. It can be easily checked that D is metric on R infinity. D is metric on R infinity. We shall prove that topology induced by D. We shall prove that topology, TP means topology, induced by topology induced by capital D on R infinity, R infinity, R infinity is precisely the product topology, is precisely the product topology on R, the product topology on R, product topology on R. Let U be an open set in the metric topology. Let U be an open set in metric topology. An open set in the metric topology. Metric topology. Metric topology. Metric topology. On X. On X. Metric topology on X. And X belongs to 0. Then there exists a positive real number R. Then there exists a positive real number R. Real number R. Positive real number R. Small number. Positive real number R. Such that the open sphere, such that the open sphere SR of X, SR of X, that equal to Y belongs to Y belongs to Y belongs to Y belongs to mod dx comma y, mod dx comma y, y less than R, less than R, less than R. These subset are equal to U. Subset are equal to U. Choosing large N, choosing large N, choosing large N, N belongs to Z plus means the set of positive integers, meaning such that 1 by n less than R, 1 by n less than R. Now let G equal to x1 minus R, x1 minus R, comma x1 plus R, x1 plus r into x2 minus r, x2 minus r, comma, x2 minus r, comma, x3 minus r, x2 minus r, x2, the extra given, x2 plus r, x2 plus r into. The printing mistake is there, you have to correct it. No need of writing x2 minus r two times. Only one time is enough.
Okay, sir.
The so on. So on xn minus r to x suffix n. N means set of natural number, nothing but minus r, comma, xn plus r plus r into so on. So on. So we shall prove that x belongs to G is subset or equal to, we need to prove that. We need to, PT means prove that. We need to prove that x belongs to G is subset or equal to union. Subset or equal to union. Clearly x belongs to, clearly x belongs to G. X belongs to G. Also if y belongs to G. Also if y belongs to y belongs to G. Y belongs to G. Y belongs to G. Then dxn comma yn, dxn comma yn, then whole divided by n, whole divided by n, less than or equal to 1 by n, less than or equal to 1 by n. For all n is greater than or equal to, n is greater than or equal to capital N. Hence dx comma y and hence dx comma y, dx comma y, dx comma y less than r, less than r, and y belongs to, and y belongs to u, when y belongs to u. Then u is open in product space r power infinity. Then u is open in the product space, in the product space, product space, the product space r power infinity, r power infinity. On the other hand, other hand, the other hand, the other hand, let W be the sub basic open set. Let W be the W be the W be the sub basic open set, sub basic open set, sub-basic open set in the product topology on RF infinity. In the product topology, TP means topology on R power infinity. Let W equal to Pn minus 1 Xn minus epsilon Xn plus epsilon. These are neighborhoods of Xn, where Pn in the nth projection R power infinity, where Pn, where Pn, where Pn is the nth projection, nth projection, nth projection, nth projection of R power n, of R power n, R power n onto onto R and epsilon greater than 0. Epsilon greater than 0. We can assume that epsilon less than 0. Let epsilon less than 1, less than 1. Then x belongs to, then x belongs to, then x belongs to S epsilon x, S epsilon x is subset are equal to W, is subset are equal to W, is subset are equal to W. Thus, every sub-basic open set, thus, thus, every sub-basic sub-basic, every sub-basic open set in is open set, open set, open set in is a member in the matrix topology, member in the member in the matrix topology or R power n is matrix topology on R power n, R power infinity, not n, R power infinity. Thus, the product topology and matrix topology, thus the product topology, product topology and metric topology, metric topology, metric topology, induced by D, induced by, induced by D, induced by D are the same, are the same, are the same. Then R power infinity is a r power infinity is matriceable. Matriceable. This completes the theorem, hence proved. Is important for 10 marks. Hence proved. Hence proved. Next, most important theorem, Euresun's metrization theorem. Page number 113. Theorem. Theorem. What is that theorem? Euresun's metrization. The question formation is state and prove Euresun's metrization theorem, or they will give statement. Any second countable normal space is metrizable. You have to identify this is the metrization theorem. Euresun's Euresun's metrization theorem. Euresun's metrization theorem. Euresun's metrization. Most important for 10 marks. Statement. Any second countable countable any second countable normal spaces normal spaces metrizable metrizable proof. Proof. Let X be a second countable normal space. Let X be a second countable normal space. Second countable normal space. NS means normal space. We shall prove that there is a embedding. We need to prove that is an embedding of x into r power infinity. Embedding means to fixing. Is an embedding of x into r power infinity. X into r power infinity means x is embedded in r power infinity set of real numbers. So fixed in r power infinity. X will be homeomorphic to subspace of R infinity. Then X will be X will be homeomorphic to R power infinity. R power infinity. And since R power infinity is a metrigeable, since R power infinity is a metrigeable, metrigeable, metrigeable. And every subspace of R power infinity, and every subspace of R power infinity is metrigeable, is metrigeable, metrigeable, is metrigeable. And every subspace of R power infinity is metrigeable. It follows that X is a metrigeable. It follows that it follows that X is metrigeable. Metrigeable. Therefore, it is enough. Therefore, it is enough if we prove that there is an embedding X into R. Enough embedding X into R power infinity. R power infinity. Page number 114. Let beta equal to Bn. Let script beta equal to Bn. Script B that is script B equal to Bn. Be a countable base for open sets. Be a countable base for open sets. Base for open sets. Open sets in X. In X. That means since X is second countable, such a base exists. Let script beta equal to. That means script C equal to. This is script C equal to B1 comma B2 belongs to script beta cross script beta script B script beta cross B script B such that closure of B1 is subset are equal to B2 subset are equal to 2. Then C is countable, we can write. Then C is C is countable. We can write we can write we can write C equal to script C equal to C1 comma C2 comma etc. So on. So where each Ci, so each Ci each Ci each Ci equal to each Ci equal Ai comma Bi Ai comma Bi, where Ai Bi are basic open sets, where Ai comma Bi are basic open sets, basic open sets, open sets, open, open sets, open sets. The closure of Ai, the closure of Ai is subset are equal to Bi. Thus far, thus far, then for each I, the closure of Ai and x minus Bi and x minus Bi, x minus Bi are disjoint closed sets in X, are disjoint closed sets in X, disjoint closed sets in X. Since X is normal, there exists a continuous mapping. Since X is normal, since X is a normal, there exists a continuous map. There exists CTS means map, continuous map. F x my x tends to 0 comma 1. F5 F5 x tends to 0 comma 1 0 comma 1 such that Fi equal to 0. Fi of A equal to 0. A equal to, for all A belongs to, for all A belongs to AI bar and Fi equal to 1 for all. Just a minute. fi of b equal to 1 for all b belongs to x minus b. b belongs to x minus b. b belongs to x minus. Now define x tends to r infinity. Now define f x to r infinity to r infinity x to r infinity by f of x equal to by f of x equal to fi of x fi of x fi of x fi of x comma f1, that is f1x, f2 f2x divided by 2, so on so on fnx divided by n so on so on so on. So we shall prove that f is required embedded of x in r power infinity. Okay. That f is homomorphism of x onto f of x. So that is f is homomorphism homomorphism on x onto f of x. F of x. If x is not equal to y, if x is not equal to y, that belongs to capital X. There exists a basic open set B. There exists basic open set B such that x belongs to B and y does not belongs to B. X belongs to B and y does not belongs to B. Y does not belongs to B. X is normal. There exists a basic open set. Then X is normal. Normal means normal space meaning. Normal. X is normal. X is normal. X is normal. There exists a basic open set A. There exists basic open set. Basic open set. Basic open set A such that X belongs to A is subset are equal to A bar is subset are equal to B. Subset are equal to B. A comma B belongs to here A comma B belongs to C. Here A comma B belongs to script C. And hence A comma B. Hence A comma B equal to Ci. A comma B equal to Ci. Where I equal to 1, 2, 3, meaning for some I, Fi of x equal to 0. Phi of x equal to 0, x equal to 0. Since x belongs to A subset are equal to A bar, A subset are equal to A bar, and Fi y equal to 1. Fi y equal to 1. Fi equal to 1. For y equal to x minus b. Thus, f of x is not equal to f of y. Therefore, x to f of x, is a bisection. Bisection means both 1, 1 and on 2 is called bisection. Bisection. Now we shall prove that f is homomorphism, and f and f inverse are continuous. We shall prove that. F is homomorphism. F is homomorphism. Is homomorphism. And f and f inverse is continuous. F and f inverse are continuous. Prove that f is continuous. We shall that prove that f is continuous. F is continuous. Prove that f is continuous. F is continuous. We shall show that given. We shall show that x naught belongs to capital X. X naught belongs to capital X. X naught belongs to capital X. X naught belongs to, and epsilon greater than 0. And epsilon greater than 0. There exists a neighborhood G of x naught. NBD means neighborhood. NBD. Neighborhood G of x naught in capital X such that D of f of x naught f of y less than epsilon. F of y is less than epsilon. F of y is less than epsilon. For all y belongs to G. That x naught belongs to x and epsilon greater than 0 already given. Choose positive integer n naught such that positive integer n naught such that S means such that 1 by n naught by n naught less than epsilon by 2. Less than epsilon by 2. Less than n. For 1. For 1. Less than or equal to n. Less than or equal to n naught. N naught. Since Fn is continuous. Fn is continuous. Fn is continuous. There exists a neighborhood G. There exists neighborhood G. En such that mod Fn x naught Fn x naught minus Fn y minus Fn y less than or equal less than epsilon by 2. Less than epsilon by 2 for all y belongs to G. For all y belongs to G. This is equation number 2. Equation number 2. Then equation number 2. Then where is the equation number 1? Equation number 1 is this one. Right. Equation number 1 and equation number 2. Equation number 2. Right. So put G equal to G equal to union I equal to 1 to n naught union I equal to 1 to n naught Gi. Then for any y belongs to G, we have d of Fn x naught comma Fn y whole divided by n that equal to minimum of Fn x naught Fn x minus Fn by modulus comma 1 whole divided by n less than epsilon by 2. Less than epsilon by 2. For all n by 1 and 2, for all n by 1 and 2, therefore d of f x n naught f x naught comma f of y, okay, equal to supremum of n d of f n x naught comma f n y whole divided by n, that is less than or equal to epsilon by 2 less than epsilon. That's less than epsilon. Thus f is continuous. Thus f is continuous. Thus f is continuous. Is continuous. It is enough. We prove that it is enough. We prove that. Prove that f of g is open. F of g is open. Is open. F of g is open. G is open. F of x is for all open sets. F of x. F of x for all open sets G in X. Open sets G in X. G in X. Open sets G in X. G in X. Let G be an open set in X. Let G be an open set. G be an open set. Let G be an open set in X. In X. And f of x naught. F of x naught. X naught belongs to f of g. So f of g means x naught belongs to x naught belongs to g. X naught belongs to g. X naught belongs to. We shall prove that there exists a epsilon greater than 0. We shall prove that there exists epsilon greater than 0. Such that S epsilon f of x naught, S epsilon f of x naught of x naught intersection f of x intersection f of x subset are equal to f of g subset are equal to f of. First, choose a basic open set B. First, choose basic open set. 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 Set B such that B such that B such that x naught belongs to B. X naught belongs to B. Subset are equal to G. Subset are equal to G. Then choose another basic open set here. Then choose another open set. Another open set A such that S means such that x naught belongs to A. X naught belongs to J. Is subset are equal to subset are equal to subset are equal to X belongs to B. Is subset are equal to here we missed one. Subset are equal to B. Another way said X naught belongs to A. Is subset are equal to closure of A. Closure of A. Is subset are equal to B. Subset are equal to is subset are equal to G. Subset are equal. Then the pair A comma B belongs to script C. Then the pair A comma B, then the pair means open sets A comma B belongs to script C. Script C. A comma B belongs to script C. Script C. To script C. Hence A comma B belongs to C and not. Hence A comma B belongs to A comma B equal to C and not. C and for some positive integer n. Positive integer n. Integer n. Positive integer n. Now choose epsilon such that choose choose epsilon such that epsilon lies between 0 and 1 by n naught. N naught is the positive integer. Then 1 by n naught. N naught. And hence D f n naught x naught f n naught x naught f n naught y f n naught y whole divided by n naught whole divided by n naught less than or equal to D less than or equal to P mod f of x naught comma f of y less than or less than epsilon less than 1 by n naught less than 1 by n naught less than and hence and hence d f n naught x naught d of f n naught x naught comma f n naught n naught y is less than 1 and this implies that and this implies that this implies that f n naught x naught minus Fn naught y, not y, less than 1, less than 1. And since Fn naught x naught that equal to 0, that equal to 0. So for x naught belongs to A, it follows that it follows that it follows that Fn naught y not equal to 1. Fn naught y is not equal to 1. Not equal. And y belongs to B. Hence, y belongs to B is subset are equal to G. Subset are equal to G. Is subset are equal to G. Subset are equal to is subset are equal to G. So recall that Fn not Z not equal to 1 for all Z belongs Z does not belong to it. Therefore, S epsilon, S epsilon, S epsilon, F of x naught, F of x naught, intersection, F of x, intersection, F of x is subset are equal to F of G, F of G. Thus, F of G is open. Thus, F of G is open in F of x, in F of x. This shows that this shows that F is an homomorphism. F is an homomorphism of x onto F of x to F of x onto F of x. Hence, thus x is matriceable. Thus, x is matriceable. This completes the proof. Hence, proof. Hence, proof. Hence, proof. Right. Next, one theorem is there. Sometimes, rarely they will ask me. No need. These two theorems is enough. No? Okay. Okay, all of you understood? These three theorems, definition. First, you need to read definition. Two theorems we discussed. These two are important for, most important is Euresun's negligible theorem. Okay.
Okay, sir.
Tomorrow we'll meet same time. Thank you very much.
Okay, sir.